Welcome to the deep dive where we cut through the noise. Today, we're diving into something big, quantum cryptography. We're going to explore how quantum computing is, well, profoundly transforming digital security.
It really is.
Our mission here is to unpack the significant threats from these powerful quantum machines and also the groundbreaking quantum-safe solutions popping up to counter them. It's a huge shift, really, moving security away from just assuming math problems are hard
Right, computational assumption.
to basing it on fundamental physical laws.
Yeah.
So what's the core idea we need to grasp right from the get-go?
Well, the key thing is classical cryptography. It's always relied on mathematical problems we just assumed were too hard for computers. The challenge now, the big one, is that quantum computers are getting ready to make those hard problems actually pretty easy.
Okay.
And that fundamentally changes the whole security picture.
Right. And this is where it gets, honestly, a bit mind-bending. To really get this quantum leap, we have to talk qubits. They're not like classical bits, just 0 or 1. Qubits use superposition.
Existing as both 0 and 1 at the same time.
Exactly, for incredible parallel processing. And then there's entanglement.
Yes, linking qubits so they act together instantly no matter how far apart.
These properties, they give quantum computers this almost scary power to, well, break our current security.
Precisely. And it's this fascinating duality, you see, the very quantum stuff, superposition, entanglement that lets them break classical crypto.
Yeah.
That's also the foundation for why quantum key distribution, or QKD, is potentially unbreakable.
How does that work?
It flips the script. It's not about hard math problems anymore. It's pure physics. You've got the no cloning theorem. You just can't copy an unknown quantum state perfectly.
Okay.
And Heisenberg's uncertainty principle means if you try to measure a quantum state, you disturb it. So any eavesdropper, they will leave a detectable trace.
Wow. So security shifts from math difficulty to actual physical laws.
Immutable physical laws.
Yeah.
Exactly.
So what does this mean for, your digital security today? Our sources flag 2 major quantum algorithms.
Big threats.
First, Shor's algorithm. It factors large numbers exponentially faster. That directly breaks things like RSA and elliptic curve cryptography, our public key encryption backbone.
Yeah, stuff that takes classical computers billions of years. Shor's could potentially do it in minutes or hours on a capable quantum machine.
Minutes! And then there's Grover's algorithm.
Right. Grover's offers a quadratic speedup. It targets symmetric key algorithms like AES and hash functions.
So it doesn't break them outright, but it weakens them significantly.
Effectively halves their security level.
Yeah.
So your AES 256. It suddenly only provides the strength of AES 128 against a quantum attacker. Needs an urgent upgrade.
Okay, that's serious. Which brings up a scary thought.
The harvest now, decrypt later problem, HNDL.
Explain that.
It means malicious actors right now are likely scooping up and storing sensitive encrypted data.
Data encrypted with today's methods.
Exactly. They're banking on decrypting it later when they get their hands on powerful quantum computers.
So long-term secrets aren't safe even if they're encrypted securely today.
Potentially not. That's why immediate action is becoming crucial, especially for data that needs to stay confidential for decades.
Okay, so counter strategies. We need them now. What are they?
2 main paths are emerging. First, post-quantum cryptography, or PQC.
PQC. Got it.
These are essentially new classical algorithms. They run on today's computers, but they're based on different mathematical problems.
Problems believed to be hard even for quantum computers.
That's the idea. NIST, the U.S. standards body, is actively standardizing these. We're already seeing algorithms like MLChem for encryption and MLDSA and SFINCY for digital signatures being adopted.
But it's not a magic bullet, right? The sources mentioned some issues.
Definitely not a one-time fix.
Yeah.
We saw the Psych, or SE algorithm, which was a contender, get broken relatively quickly. Yeah, it's a stark reminder. This is still a bit of a cat and mouse game. Organizations need what we call cryptographic agility, the ability to swap out algorithms if needed.
Okay, so PQC is one strategy. What's the second?
That's quantum key distribution, QKD, the physics-based approach we touched on.
The one using actual quantum properties for security.
Right. It offers information theoretic security. In theory, it's unbreakable because its security is baked into quantum physics itself. Plus, that inherent eavesdropping detection is a huge advantage.
Sounds amazing. But there have to be downsides.
Oh, absolutely.
Yeah.
Significant practical limitations.
Sure.
Distance is a big one, typically only 100 to maybe 500 kilometers over optical fiber right now.
Okay, so not great for long-haul communication.
Not easily. It's also expensive, needs specialized hardware, key generation rates can be low, and it's a critical apostasy. QKD itself doesn't provide authentication,
Mean.
meaning you know your key is secret, but you don't necessarily know who you exchanged it with. It's vulnerable to man-in-the-middle attacks unless you pair it with strong authentication, often using PQC or pre-shared keys.
Ah, okay. So given these pros and cons for PQC and QKD, what's the way forward?
It looks like a hybrid approach is the most pragmatic path, at least for the foreseeable future.
Mixing and matching.
Yeah.
Yeah.
Use QKD, where its physics-based security is absolutely paramount, like for super-sensitive point-to-point key exchange, maybe between data centers.
And PQC.
PQC for broader applications, software updates, digital signatures, general encryption where you need something deployable on existing infrastructure.
Makes sense. And the sources hinted at even more advanced stuff. Exotic quantum crypto.
Yeah, some really mind-bending ideas down the road. Things like quantum money, unforgeable digital cash, thanks to that no-cloning theorem,
Wow.
or quantum homomorphic encryption, which would let you compute directly on encrypted quantum data. Imagine the privacy implications. These could enable entirely new ways of interacting securely.
Okay, stepping back, looking at the big picture here.
This transition, moving our entire digital world to be quantum safe, it's massive, a complex global effort that will likely take decades.
Not just a tech upgrade, then.
It's not at all. It demands huge economic and strategic investment across, well, pretty much every sector. So thinking about that, what's a proactive step you can maybe take today, even just to learn more?
That raises a really critical question for everyone listening. How will vital industries, think finance or healthcare, the ones handling data that needs to be safe for decades, how will they accelerate their transition, especially with that harvest now, decrypt later threat looming? Something for you to chew on and maybe explore further as you continue your own deep dive into this really fascinating frontier.